get started here from current slide. There we go. I don't know if, okay, we did agree, or y'all wanted to go until 7 tonight, right?
Yes.
Okay, good. All right. So to make sure I wasn't wrong on that. Okay, now, what question do you have?
I just want you to do examples for the ones I did like.
Okay, well, did you find examples in the book like it?
Yeah, but
Well, tell me which one.
I'd rather you do it because actually hearing it did for you.
Well, I mean, I don't know what ones you're having problems with, so I don't know what examples to suggest.
Can you do something similar to
Number
number 3?
3. Coefficient of sliding friction. Okay, this is back from chapter 5. Okay. .4. Okay. Okay, if I'm reading it correctly, number on page 134, problem set 5.4, number 6, I think is similar to number 3. Would you agree? Yeah. Yeah, they give you the coefficient of sliding friction. This is a different one, and it's kinetic friction here, but it's the same deal. The motor driving can deliver a maximum force, and it says what is a winch with a 450-pound capacity, so that's the same type thing. Now theirs are in newtons. What's that?
Number 7 would be more accurate because it has the pounds.
Okay, well, yeah, we can do it in pounds. Okay, and it's rolling friction, but you just substitute the friction that you need. Okay, so yeah, let's do number 7. Page 134. Get my pen set up. Have to keep an eye on my computer to make sure it keeps charging. Okay, this is page 134. Problem set 5.4, number 7. All right. Here, a tow truck can deliver 2,500 pounds of pulling force. Now, I'm not going to draw the tow truck, but I'll just put the force here. Here's a pulling force of, I'll call it pulling force of 2,500 pounds. Okay? What is the maximum weight the truck can be pulled, maximum weight truck that can be pulled by the tow truck? So here's the road here, and here we have a truck. It's just going to be a box, but that's going to be your truck. Okay? So what's the maximum weight truck? So we want the weight F sub W of this truck. Now that weight is going downward, right? Okay? Pulled down by gravity. Okay? Can be pulled, and that's the question. That's what we're looking for. Just like number 3. That can be pulled by the tow truck if the coefficient of rolling friction, now the coefficient, okay, your frictional force is always against the motion. You're trying to pull it to the right, so the friction is doing here. So here's the force due to friction. And the force due to friction, if you flip back a page there, the general definition formula is on page 132. This force due to friction is your mu, the coefficient, times the normal force. Okay? Now, what is the normal force? The normal force is the force that is acting in the opposite direction of the weight. Weight is pulling downward, normal force is pulling up. So this is your normal force here, and that's going to be the same as your weight because this is a level thing. It's not going through the road, it's not flying off the road, it's sitting on the road and moving. So the normal force in this problem will be exactly the same as your weight. So if we can find that. Now, this force due to friction has got to be exactly equal to your pulling force because it's asking for the maximum weight that can be done. So this would be the maximum friction. So this is your, this and this are equal. So now we have 2,500 pounds is equal to your mu, and they told you here the coefficient of sliding friction, or rolling friction in this case, yours was otherwise, this is 0.10, right? Oh, I'm on the wrong page, that's why I can't see it. 0.10. Okay, so that's 0.10 times your normal force. Now, if we can figure out the normal force, that's going to be the same as the weight. It's just in the opposite direction. Okay? So, how do we do that? You're looking for this normal force, which is going to be the same as your maximum weight. Divide. Divide both sides by 0.10. Okay? No units on the coefficient of friction, and when you divide by that, that moves the decimal one place to the right, so that's going to be, in this case, your normal force is going to be 25,000 pounds. So that's the maximum weight of the truck that this tow truck can pull. Okay? Now, they didn't put any bars over 0, so we only have 2 significant digits, and that is 2 significant digits. Okay? And this is also the weight, F sub W, and that's what you're looking for. Now, that one is an odd problem, so it's in the back of the book. Is that the answer they had back there? Brianna is here. All right. I have a mark somewhere back here. This is 5.4. Is that right? Yeah, number 7, 25,000 pounds. Does that help?
Yes.
Okay, good deal. Were there others?
It was number 6.
Number what?
Number 6.
6? Okay, let me find out what number 6 is. Yes.
Is it okay if I turn mine on Thursday?
Oh, sure. Yeah, there's no.
Turn mine on Thursday too.
Yeah, that'll be fine. Number 6, oh, let me go on and clear this off the screen. All right. A cyclist and her bicycle, combined mass of 75 kilograms, apply a force of 34.2 newtons. If the frictional force is minus 23.5 newtons, what will the acceleration be, the acceleration of the bicycle? Okay? Now, it's also a friction problem. And we have no coefficient of friction mentioned here, so we don't have to deal with that. Okay. That's coefficiency. Okay. Now this is going to, what's that? That's exactly what I was looking at. Number 15 is going to be the closest. At least one of those, A, B, or C, will probably, yeah, the B part will be like that. Okay? Okay, this is number 6. Right. All right. So let's do, this is page 135. Same problem set. And by the way, Brianna, this is problem set 5.4. And this is on page 135, and this is number 15. We'll do the whole problem, but the B part is the one that's closest to number 6. Okay? Rubber tires and the 15, yeah. Rubber tires and the wet blacktop have a coefficient of kinetic friction of 0.5. A pickup truck with a mass of 750 kilograms, that's 3 significant digits there, traveling at 30 meters per second, skids to a stop. Okay? Now that is very different from the problem we have, but we'll, number 6, but let's go on and do that first. A, what are the size and direction of the frictional force that the road exerts on the truck? Okay, that's not what we're dealing with, but let's go on and figure that. So here we have a pickup truck. Now here's going to be our road here. Coefficient of kinetic friction is 0.5. Pickup truck with a mass of 750 kilograms is traveling at 30 meters per second, skids to a stop. So here's the truck. I'll not make it a very fancy truck, just a truck. There's the truck, okay? It has a mass of 750 grams. The mass of the truck is equal to 750 kilograms. Okay? Traveling at 3.0 meters per second. So that's its initial velocity. V sub I is equal to 30.0 meters per second. Okay? Skids to a stop. So somewhere over here, it now has applied the brake and has skidded to a stop, same everything, but over here, the final velocity, Vf, is equal to 0 meters per second because it came to a stop. Okay? Now, the force, this is a little bizarre on this problem. The force is in the opposite direction because it's changing the velocity. So the tires in the road are pushing in this way. So the force required to stop it, okay, I'll put the stopping force, is in that direction. Okay? That means the frictional force is in this direction. F sub F is in that direction, and that's going to be mu times your normal force, just like we had, oops. I'm used to calling it N, but this book calls it F sub N. Okay, F sub N. Now they told us mu was 0.5. 0.500. Okay? Now, what is the normal force? The normal force is the force of the road up on the vehicle, right? And because the vehicle isn't falling through the road or flying off the road, that's exactly equal to the force due to the weight. So this is your normal force, and here's your force due to the weight. And these things in this problem are equal. Okay? We've got enough information to calculate this weight of the truck. What would it be? Any help? Huh? How do you calculate the weight of the truck? What is weight? Okay. 750. Okay. It's the mass times the what? Acceleration due to gravity. A force is always the mass times the acceleration. Weight is the mass times the acceleration due to gravity. So we can calculate this. This is 750 kilograms. And what's the acceleration due to gravity? The acceleration due to gravity. No, what is the acceleration due to gravity? In the SI units. You know that. 9.80, I believe it is, isn't it? And what units? Yeah, I know. But what are the SI units for acceleration? Meters per second squared. Perfect. Okay? Now, so multiply those two together, and you get something on the order of 7,400 and something. I probably could do it in my head, but I don't want to. No, I can't do it in my head. I could, but I'm not going to put that much in. Say again? 250? 350. Okay, I guess too high. 7,595. Whoa, that's not right. 7,350, is that what you got? Okay, and this is what unit? It's what? I can't hear you. Okay, that was an acceleration. This is a force, a weight. It's kilogram meter per second squared. No, kilogram meter per second squared. But what is a kilogram meter per second squared? A newton. So that's 7,350 newton. Now I'm assuming you got that you did it right. That sounds reasonable. Okay? Now, that's also the normal force, 7,350 newtons, because this is a flat level road. Okay? And that's what we enter here. And now we know the force due to friction is 0.500 times that normal force, 7,350 newtons. And that will be exactly half that, which is 3,675 newtons. Except that's too many digits. But we're going to hang on to them for now. That's the force due to friction. Okay? I'm sorry? It went really smoothly and well. Had a long wait. They didn't have me. They had called, we had made up arrangements, everything else, but when I got there, they said, you're not on the list. And I was there at 5:30 in the morning to be told I'm not on the list. They said, well, just wait till someone gets in, we'll find out. We can tell you're on the list somewhere up there, but you're not on the list down here. So I had to sit there for an hour. Everybody else that came after me went on up and went wherever they needed to go. My wife and I sat there for an hour and finally said, okay, you can go on in. They found you're on, they forgot to send your name down or something like that. So anyway, once that happened, then it went really smoothly after that. There was a bit of waiting and stuff like this, but it was normal, and they were really good. And they took me into the place, and they said the anesthesiologist was putting some things in to do this, that, and the other with. They had already done it, had put an IV there, but at some point she must have given me some anesthesia. And the next thing I knew, they were talking again. I thought, well, when are they going to get started? I didn't ask that. They said, oh, we're through. So my wife said it was less than 30 minutes, It just really done. And I didn't have any problems after that, except I slept all day Thursday. I mean, I was lying on the couch. I was planning not to sleep, but my eyes were dilated, so I had to wear sunglasses all the time, even inside, because that made my eyes hurt. And my wife would put the drops in my eyes, and I'd fall back to sleep. And I just slept basically all day long. And then went to bed that night and slept. I had to wear a shield over my eye, but everything went well. Now I don't have to do the shield anymore. I can lift up more than 10 pounds. I can bend over. I can do everything I couldn't do before, so it's good. All right. Up to where we all need to be? You say wait. Okay. So this is your frictional force, 3,675 newtons. Now that's too many significant digits, but let's hang on to them for a while. Okay? It says, what's the size and direction of the frictional force that the road exerts on the truck? The size is this. The direction is forward, not in the direction of stopping, but in the direction forward. The frictional force always opposes the change of motion. Okay. So is that what they got in the back for the A part? That's not important, but it's 5.4. The sign indicates friction acts in the opposite direction of that of the truck. Yeah, that's all they say. Okay? So, that's the A part. Okay, the B part. Find the acceleration of the truck. Now, I think this is similar to what number 6 is. Okay? What would be the acceleration of the truck? Okay? Well, the frictional force is exactly equal and opposite to the stopping force. Okay? And the stopping force, this will be F. The stopping force is going to be the mass of the truck times the acceleration of the truck. Newton's second law. Okay? We know this is the stopping force. It's just in the opposite direction. We know the mass of the truck, so we can calculate the acceleration how? By dividing what?
I keep looking at my own test.
Okay.
Dividing it,
Stopping force by the mass, right? Divide both sides by m. You're trying to isolate the acceleration. That's what we're looking for. So divide both sides by m. Now, what is your force? It's 3,675. What is a Newton? Kilogram, meter per second squared, divided by your 750 kilograms. And here the kilograms go out. So take your 3,675 and divide it by 750. Looks like it's going to be something between 4 and 5, I would guess.
what did you just write
Okay.
there?
Right here. Okay. There was the A part. That gave you the frictional force here of this. Well, that frictional force is exactly the same as your stopping force. Frictional force is this way, stopping force is that way. Okay? Just opposite direction. So this is the same as your stopping force. So that's what goes up here, your stopping force. Stopping force is your mass times your acceleration. That's what we're looking for, is the acceleration. So, since we know it's mass times acceleration, if we divide both sides by the mass, that will isolate the acceleration. So the acceleration is the stopping force divided by the mass. Stopping force is 3,675 newtons, which are kilogram meter per second squared, just like here, divided by 750. That was the mass of the truck, 750 kilograms. And the kilograms go out, so 3675 divided by 750, I'm guessing around 4 to 5, what you get. What you get is acceleration. My guess may be off. Yep, right in between 4 and 5. Get it? 3,675 divided by 750. .91, and that would be meters per second squared. Perfect. There's your acceleration. Now the book has how far will it travel. Your problem doesn't have that. We can go on and work it if you need to know that, but it's up to you. Huh? Okay. All right. So there is the one like number 6. Number 7. Okay. Okay. All right, to erase, so y'all got that one done? 1 second. Okay. I got time. Whoa! Got it? Sorry, I have to do all over the page because I don't have a lot of room. It keeps sounding like it's going to rain. And, oh, is it? Okay. And I had to park record distance from the building here because all those places were filled out there. Usually I get to park relatively close, but today I had to park way down, so I'm hoping it eases off by 7 o'clock. Okay. What's that?
I have to go all the way to Trussville.
Oh, yeah.
I come one way and then keep going to the other way. I'm done. Thank you so much.
All right. Everybody got it? All right. And next you said was number 7?
Yes.
Okay. Now, number 7, I don't know if there's an exact duplicate. Small railroad engine is able to exert 175,000 pounds of pulling force. Coefficient of friction for steel wheels on steel rail is 0.7. Now, here is where you just have to change your question a little bit. The question is, how much weight can the engine pull on the level track? And this is very similar to the one we just did, isn't it? Number 7. Right? I think it's now coming down fully. Okay. So your question is, how much total weight can that small railroad engine pull? And then once you know the weight, divide 45,000 into that, and that'll tell you how many cars it can pull. Does that make sense? Okay. Now, don't round up. If it goes 6.9 cars, it can't pull 7 cars. It can only pull 6. Okay. If it's 3.2 cars, it's going to be 3 cars. Don't round up. Always, yeah. Okay. Because you see, they're not going to have a fraction of a rail car. So it can only pull so many. Does that make sense? Okay. Any number what? 9. Okay. All right. That is the reactive force, which is law of action and reaction. Let's see where those will be. All right, the 5.6 doesn't have any specific problems. Well, let's see, maybe 5.5 will do us. Let's see. Let's just draw out number 9, because I don't see one that's just like it. Do y'all see one that's anywhere close? Okay.
It's a sample on 149.
Page 149. Wow, that's in a different.
Is that the sample?
Yeah.
One like it.
Yeah. Okay, that's in the momentum chapter, which is legal. You have the whole book. And yeah, that does do it. Yeah, momentum, though we haven't actually done that. But let's just take a look at number 9. Here is your water, okay? And here's the rowboat in the water, okay? Here's the dock, okay? Now, a 64 kilogram person steps off the rowboat, okay? The mass of the rowboat is 129 grams, kilograms, yeah. The mass of the person is 64.5 kilograms, okay? The 64.5 kilogram person steps off of a 129 kilogram rowboat. Let's bring the dock down a little bit, maybe to here, so it's an easier step, okay? Here's the dock, okay? Steps off the rowboat with a force of 34.0 newtons. So when he steps off, he's pushing against the rowboat with the force of his step, let's call it, is equal to 34.0 newtons. Okay? What is the force that is applied to the person by the rowboat? Now, this is the person, the force by the person on the rowboat. So what you reckon the force of the rowboat on the person is?
64.
I know, right? It has nothing to do with it. That would have to do with acceleration. But if I'm stepping here to push myself here, I'm pushing on the floor with a force of 34 newtons. What is the force pushing against me with? If I push against a rock or a desk with a certain force, what is the force that the rock pushes on me?
129.
Okay. Okay. Go back. Don't mess with conservation of momentum here. Let's just look at the statement. Law of reactions is on page 138. For every force applied by an object A, the person, to object B, the rowboat, there is an equal but opposite force exerted by object B, the rowboat, to object A, the person.
So if you push it, it's pushing back. So it's
If he's pushing with a force of 34 newtons, guess what the rowboat's pushing? With 34.0 newtons, just in the opposite direction. There really were no calculations at that. That's just understanding the third law. Sorry. I gave it away. Okay? You see? I mean, that's all there is to it. It has to be equal and opposite. Okay? Is that okay? I'm sorry. I wish I could find one that we could have done something else, but I should have just gone straight to that and say, there's your answer. Okay. But I don't know. Is that all? Okay. All right, glad to. All right, then let's clear the screen and we'll go back to where we left off last time, which is Chapter 8, Work and Energy, 8.2, which is Power. And let me clear the screen. And we're doing example 6. A pump is needed to lift 1,500 liters of water per minute, a distance of 45 meters. Okay? So here we've got, one of my students this morning said he had left the garage door open and it rained and water flooded his basement and he was late getting to class because he had to get all the water out because he didn't have a pump that could do this for him. So here's a pump needed to lift. So I'm just going to draw a pump down here. And it's going to need to lift water. It's pumping water out of, say, your basement, but it's having to go up high. Why they have to go this high, I don't know. Maybe this is a really deep basement. It needed to lift 1,500 liters of water. I think the bar is over the first zero there. Liters of water, okay, per minute. 15 liters of water, and this, by the way, is water, H2O, per minute, a distance of 45 meters. So it's having to lift it way up there. The, what do they call it? S is equal to 45.0 meters. That's a long way. What is the power in kilowatts must the pump be able to deliver? And then they give you a little hint here that 1 liter of water has a mass of 1 kilograms. Okay? Okay? So that changes your problem here. You're lifting 1,500 kilograms per minute. Okay? Now, the question asks for what power the pump has to be. What is the power of the pump? Can anyone remember what power is? I know it's been a whole week since we last met. What is power? Rate? Rate of what?
The rate of work.
Okay, energy per unit time, or work per time. Work or energy per unit time. That's what power is. Okay? Now, what is work or energy? Let's deal with work. That's probably easier. So, yeah, force times a displacement per unit time, because work is force times displacement. Okay? Well, what is force?
Force times
What is force? Yeah, in SI units, what is force? Or is in everything, the formula is the same.
8.9. I mean, it's a 9.8.
Okay, it's the mass. So this is mass times acceleration due to gravity, because this force we're talking about is the weight of the water. Okay, so it's mass times acceleration due to gravity times displacement divided by time. That's going to be your power. Okay, well, we already know what the mass per unit time is. That's it right there. The only problem is we've got that in minutes and we need it in seconds, right? So we need to do a unit conversion to get kilograms per second. So what are we changing? Now remember, when we do a unit conversion, I put two blanks here. This blank is for numbers. This blank is for units. Which do we put in their place first? Always put the units in their place. So what unit is going to need to go on top and bottom? See, the kilogram's not changing. So you're not changing the kilogram. You're changing minutes to second. So one's going to go on top and one's on bottom. Which goes where? We're changing that unit. Either minute or second goes on top, the other goes on the bottom. What goes on top? The minute's on top. And seconds on the bottom. That way the minutes can cancel out and you're left with kilograms per second. So now that you got the units in the right place, now match the numbers with the unit. How many minutes in a second or how many seconds in a minute? What is that?
Minutes per second, 336.
You mean
36 seconds in a minute.
Okay, is that right? Is that right? Have you got a watch that you can watch that? It takes 300 and...
Oh, it takes 60 seconds.
60 seconds to make a minute, okay? 60 seconds is 1 minute. Match the units with the numbers. So that means we're going to divide this into that. I've already wiped out a 0, and I know that 3 will go into 6. Well, 6 will go into 150. 6 will go into 15 twice with 3 left over. That would be 25. So that is 25. No, is that right? Yeah, I think that's right. 25 kilograms per second. And it's probably 25.0 kilograms per second. So that's your mass per unit time. So this will be, yeah, that would be 25.0 kilograms per second times what's the acceleration due to gravity? Help me, somebody. You know it. Acceleration due to gravity. Second? Okay. Your mass per unit time is this thing. Kilogram per second, 25. So I'll put 25 kilogram per second, 0.0. Now I need the mass to multiply by it. What's the G? What is G? That's 9.80. It's not grams, 9.80. The acceleration due to gravity. What's acceleration measured in? Meters per second squared. And then we multiply by the distance. How far are you lifting that? How far are you lifting it? 45 meter, 0.0 meters. You're absolutely right. Okay? So let's see what we've got then. A kilogram meter squared per second squared, that's a joule. And a joule per second, that's a what? A watt. You got it. Okay? So multiply those together. 25 times 9.80 times 45, and that will be how many watts you have. So times 9.8 times 45. $25 times 9.8 times 45. 936. What units? You just told me. What units? Watt. Okay. Now, two things. First, they want it in kilowatts. So how can you express that in kilowatts? Okay.
I got 22,932.
32. Okay, I'm sorry. I thought you said 6. I don't hear well.
So, do I...
Wait. Don't worry yet. 32. Okay. Now let's convert that to kilowatts. How would you do that? Okay, perhaps. This is 22,932 watts. What is a kilowatt? A kilo anything is? Yeah. It's how many watts? Not 1 watt, because they're different units. A kilo means 1,000. So if this is 22,932 watts, this would be how many kilowatts? Just move the decimal 3 places. You said 22,000. That would be 22.9. Okay, that's 3 digits there. Look to the right. That's a digit smaller than 5, so forget about them. This would be kilowatts. 22.9 kilowatts. What do they get? Oh, it's here in the book. What?
Is it not right?
They say not. Let me see. Okay. All right, maybe I did a mistake when I did my, if y'all do this, Do 1,500 divided by 60. See what you get. I may have messed up my math there. You get 25. You do 25 times 9.8, that would be about 2,000. Okay, do that one more time. What are you? 25 times 9.8. That's going to be something like 240 something. Okay, and multiply that by 45. 11,000. Where did you get the 22,000? All right. All right. Whoa. 11,025. Okay, let's do that again. Hold on just a second. Okay. 11,000 what?
11,000. Wait a minute. 11,025.
0.25?
0.25.
Okay. Watts. And then convert that to kilowatts.
Oh, take my decimal. So
Yeah.
11.
11. And you need one more. 0.0. Look to the right. That's less than 2. Forget. Throw it away. So 11.0 kilowatts. That's what they got. All right. We got awfully close to twice that. I don't know how, but we did. All right. Good deal. That finishes 8.2. I think I gave some of these before as homework exercises. I would do either 1 or 3. And then I'd do any of the odds 5 through 25. Okay? There's a lot of different ones there. Do some of each type. Okay? Got it?
Wait a minute. So what'd you say?
I'm sorry.
What did you say?
Okay, this is on page 213. Do either 1 or 3. And then any of the odds 5 through 25. Okay? And I would do some of every type of them that they have there until you get comfortable with it, then move on to something else. Okay? Yeah, but you don't have to do all those, but do some of those. All right. Ready for energy? Got the energy you need for energy? All right. Now, I think I intimated earlier that energy and work were related. Okay? Energy is defined as the ability to do work. And there's another way to say that. Work basically is the transfer of energy, is the useful use of energy. Okay? So they are very, very similar. Now, here's a problem with energy. It's a pretty simple concept. Here's the problem with it. The total energy of a system is always the same, always conserved. Okay? The trouble is, energy can change forms at the drop of a hat. I mean, it just changes form so easily. There are many forms of energy. There's mechanical energy. That has to do with the energy of moving and stuff like that. There's electrical energy. There's thermal energy. There's fluid energy. There's chemical energy. There's atomic energy. And there's sound energy, which y'all will be dealing with in sonography. Okay? That's all has to do with energy. Now, let's take the first one of those. Mechanical energy of a body or a system is either due to its position, its motion, or the internal structure. Now, they don't really define that internal structure very well, but here's the deal. I'm holding this book. It has a certain amount of energy right now due to its position. If I were to raise the book up to here, do you think it has more energy or less energy than it did when it was down here? less up here. Okay? Let me have your foot for a moment, and I'll drop the book on your foot from down here, and I'll drop it on it from up here. Now, which do you think is going to feel? It's got more energy up there. A lot more. Why does it have more energy? Because I had to do work to get it up there. So I added energy to the system. That's the energy due to position. That is often called potential energy. So potential energy, I'm going to write down some of these things. Energy is the ability to do work okay? And one form of energy is potential energy. And that is the energy due to position. Now, there's many forms of potential energy, and we'll talk about those in a little bit. Now, a second form is kinetic energy. Okay? That's the energy due to motion. Okay, in my hypothetical situation there, when I was going to drop the book, I was no longer going to hold it up there, keeping it at that energy level. I was going to let it fall, and as it fell, when I first dropped it, what was its velocity? When I release it from rest, what was its velocity? Help me. When I first let go, what was its velocity? I didn't throw it, I just released it. What was its initial velocity? Zero, because it was at rest. But as it falls, it picks up speeds and picks up speed. Now we're going to gauge the speed by the sound that it makes, okay? Okay? I'm going to hold it just maybe a couple feet off the ground. Okay, that was pretty loud, wasn't it? May not work too well. Let's hold it from here. Whoa, that was even louder. Okay? Let's do it from here. Okay. It's getting faster and faster the further it falls. So it's losing potential energy, the energy of motion, and gaining kinetic energy, energy of position, and gaining kinetic energy, which is the energy of motion. Okay? I shouldn't treat my book so badly, should I? Okay. Yuck. I hope I didn't damage that any. All right. Now, they talk a little bit about another type of potential energy, and this is the one due to internal structure, and that's called internal potential energy. Now, that's sort of a nebulous word, internal potential energy. Okay. Now, that's determined by the nature or the condition of the substance. For instance, gasoline is a bonding of carbon, hydrogen, oxygen. Okay, it's mostly carbon and hydrogen. It's a hydrocarbon, and the reason it's explosive or burns so easily is when those bonds that hold it together are released when you add heat to it, they give off lots of heat. So that is the internal energy, internal potential energy of that. I call that internal chemical energy. Now let's take another example here. Look out at all those green trees out there. Don't look out too long. Okay. What they're doing, the chlorophyll in those green leaves are capturing energy from the sun and converting that energy into chemical energy as it stores. It takes those little leaves have pores underneath them called stomata that breathe in air. And they pull in carbon dioxide from the air, and they take up water from the roots, and they just got a fresh dose of it just now. So they're pulling up water from the roots and carbon dioxide from the air, and they are forming simple sugars. Okay? That is storing internal potential energy. Now those sugars are further chemically processed by the tree to form cellulose, which is a complex carbohydrate made up of carbon, hydrogen, and oxygen. Carbon and oxygen from the air, from carbon dioxide, and hydrogen and oxygen from the water, H2O. So they're storing that, and then later you can burn the wood and give off that heat. So that energy from the sun was captured by the leaves, changed into stored chemical energy, internal potential energy of the leaves, stored chemical potential energy, changed in a sense to wood. Later the wood will be burned and it gives off heat. Okay? So you see energy is just changing all the time. The total energy stays the same, it just changes its form like crazy all the time. Okay? Another form of this potential energy, the one I was just showing you, the energy due to position, that was the gravitational potential energy. When it's up here, it's higher. Down here, it's lower. So it has different gravitational potential energy. So I call that, well, that's just right, gravitational potential energy. That's the energy due to height above the surface of the earth. Okay? So that energy is called, the book calls it E sub P. I wish they call it E sub GP for gravitational potential energy, but they leave off the G and just call it E sub P. Okay? So I'll do that too, but understand that's talking about gravitational potential energy. Later we'll talk about other forms. And that gravitational potential energy is mgh. There's the formula for it. Now, if that looks a little bit familiar, that's because that's exactly what work is. Work is force, mass times acceleration due to gravity, times the distance. We called it S in the last section. They're calling it H here. We're not calling it work. We're calling it mg, which is weight, which is, the mgh is the work, okay? Okay. mgh is the gravitational potential energy. It's so similar to work, and work was force times the displacement, F times S, but the force was the weight, which is mg. So the m's the same, the g's the same. The only difference is when we're talking about work, we call it S. When we're talking about potential energy, we call it H. That's just how far it moves. Same thing, it just uses a different symbol for it, S or H. They're the same formulas. It's just now we're talking about gravitational potential energy. The M is the mass, the G is acceleration due to gravity, which again is, 9.80 meters per second squared, or 32.2 feet per second squared, depending on which unit you're in. And the H is the height above the reference level. Now there we have another issue, okay? Whenever you talk about gravitational potential energy, you have to designate what's your reference level. If I'm holding the book over the tabletop here, and I'm going to drop the book onto the table, but that's as low as the book going to go, then this would be my zero reference level. But if I moved out here, I need to make the floor the zero reference level. But if I moved to the window and held it out the window, then I need the ground to be my zero reference level. You have to figure out in the problem what your zero reference level is. How low is as low low is the book going to go in this problem? That is your zero reference level, and then do all your calculations from there. Because the same height would be a small gravitational potential energy here, larger here, and way larger if I held it out the window. So you have to determine what that is. And your height is the height above that zero reference level. Okay? So that's what they call the height above the reference level. Okay? Now, they have a picture in the book of this crate sitting on the floor and then sitting up here. Now, they don't tell you how it sits up here, but it's been given more gravitational potential energy because the mass of the crate times the acceleration due to gravity times the height that it was listed, that is the additional potential energy of that crate. Okay? All right, to move on? Okay. And if that looks similar to work, that is almost the same formula for work. And the units, by the way, are the same. Kilogram, whoops. The units are kilogram, meters per second squared, times meter, which is kilogram, meter squared, per second squared, which is a joule. A joule measures work, a joule measures energy. Now, in the U.S. customary, mg is pounds times feet, and that would be foot-pounds. So potential energy, or any energy, is measured in foot-pounds in the U.S. customary, and just like work was measured in foot-pounds. Okay? So, let's go to example 1. Can I erase, or are y'all still writing? Let me know. Okay. All right. Now, driving myself nuts here. They're leaving stuff all over the place today. Oh, there it is. Just trying to keep track of time. Okay. All right to erase? Okay to erase? Okay. So here's example 1 on page 215. A wrecking ball of mass 200 kilograms. There's your wrecking ball. It should be, it's example 1, top of page 215. Okay? The mass of this wrecking ball is 200 kilograms. Okay? It's poised, it's being held here, poised above a surface down here, concrete platform, and this height here is 4.00 meters. Okay? Above a concrete platform whose top is 2 meters above the ground. Okay? So this here is 2 meters, 2.00 meters above the ground. This is the ground down here. This is the concrete surface. And the concrete surface is 2 meters above the ground. The wrecking ball is 2 meters above the concrete surface. Now, with respect to the platform, what is the potential energy of the ball? Gravitational, I'm going to put GP. I like to put GP, well, gravitational potential energy. The book calls it P. I just like to call it GP. Okay? What was that formula? Oh, it was so long ago. We just did it. Last slide. If you got your book, it's on the previous page. Huh? Is what?
What did you ask us?
What is the gravitational potential energy? What's the formula for it? M G H. Perfect. What's M?
Mass.
The mass. And what's the mass of this ball?
200.
200 kilograms. What's your G?
Work.
Acceleration due to gravity, which is?
4.
What?
Wait a minute. Oh, you asked him with
The G.
You told us gravitational energy, right?
Okay. Gravitational potential energy is E. Okay. M is the mass. G is what?
Weight.
No, G is not weight. mg is weight.
Okay.
What is G?
Some type of energy.
No, it isn't.
Gravity.
What gravity? It's not gravity itself, but it's the, well, we say it every time, acceleration due to gravity, which is? How do you get that? Where are you getting your 4.8?
I said 9.80.
9.80. Okay, 9.80. I'm sorry, I can't hear. What units? Meters per second squared. And what's your H? Above the platform.
Work.
What's the H? Above the platform, that's your 4 meters. This is the H above the platform. 4.00 meters. Okay? Multiply those together, and you get, that'd be 800 times 9.8 would be 600? I'm doing it in my head, so tell me if I'm right or not. 200 times 9.8 times 4.
I got 27.
Whoa, really?
If you multiply, oh shoot, you said add, right?
No, add, multiply. Those things are multiply.
700.
Say again?
I did 700 times 1,000.
Wait. No, that's a 200. 200 kilograms. Your mass. 200 kilograms times 9.8 meters per second squared times 4 meters.
7,840.
Oh, 840. Okay. I was guessing. 840. What units? Say, okay, you got kilogram. Meters times meters would be meters squared per second squared. But what is that? What? What's a kilogram meter squared per second squared? Also known, kilogram meter per second squared is a Newton, and a Newton meter is a joule. Okay. That's supposed to represent joules. Okay. It's not much of a joule. Okay. Now, if I think that number is too big and I want to make a smaller number but a bigger unit, what could I put there? Okay. Move your decimal. And what would that give you? 7. Move the decimal 3 places. 3 places represent 7.8 for what? Say again? There's 7,840 joules. Wait. Okay. What I've done is made this big number into a smaller number. That means I have to put a metric prefix in front of the joules. Which one? What represents 1,000? Say again? What represents 1,000? Which metric prefix represents 1,000? We went through this a little earlier today.
The watts.
Huh?
The watts.
Okay, watt is a unit of power. But we're going from several thousand watts to 22 or 11. Went from 11,000 watts to 11, what metric prefix? Means 1,000.
Pound. No.
No.
It ain't pound. It's watts.
Okay. Okay. All right.
Kilowatts.
Kilo means 1,000. So this would be kilojoules. Whenever you go from thousands to units, you're told to so many kilo whatever. Kilojoules, kilowatts, kilometer, whatever. Okay? Whatever you want to kilo. No, sorry. Okay. So that's your gravitational potential energy of the ball above the concrete platform. That was the A part. The B part says, with respect to the ground, this is the ground down here, this is the platform here. With respect to the ground, what is the potential energy of the ball? Well, the gravitational potential energy, P, gravitational potential energy, same formula, mgh, and the mass is the same, 200 kilograms. G is the same, 9.80 meters per second squared. But now what's the height above the ground? Okay, don't multiply anything.
Oh, the height. The height, 4.0.
Okay, that was above the platform. What's the height above the ground?
Is it 200 kilograms?
Okay, no. We're talking height. Height of the ball above the platform was 4 meters. How far is the platform above the ground? 2 meters. So now what's the height of the ball above the ground? 6. Perfect. That would be times 6 meters. The height above the ground. 6.00 meters. You add the 4 and the 2. How high is it above the ground? If the platform was 2 meters above the ground and the ball's 4 meters above the platform, that's a total of 6 meters above the ground, right? So now we multiply those together, and what do we get? Be 11,000 and something. I'm going to guess
11,800.
what's that?
11,800.
11,800 even? Okay. What units? Joules, exactly. And if you wanted a smaller number but a bigger unit, what would that be? Say again? 11.8 kilojoules. Kilo means 1,000. This is 11,000 joules. That would be 11.8 kilojoules, right?
I was trying to round up again.
No, don't be rounding. You just move your decimal. Okay? All right, let's see how the book did. They didn't change to kilojoules. They left it at 7,840 joules for the first part and 11,800 joules for the second part. All right, so that was gravitational potential energy. There is another kind of energy, as we had on the last slide, but I have to erase them so it's already gone. Other than gravitational potential energy, that's the energy of position. The energy of motion was called what? Energy of motion. Gravitational potential energy is the energy of position. What is the energy of motion? Think back to our friction. We had static friction, or we had, say again? Kinetic. So kinetic energy, and I think the book calls it E sub K for kinetic energy, its formula is, now I'll talk about the 1/2 in a minute, mass times, if an object's in motion, that means it has to have a velocity. So it's 1/2 mv squared. There's a formula for kinetic energy. Now, I think I mentioned this in an earlier context, that a lot of times in physics, if you have your main variable, velocity, squared, then you're going to precede that by 1/2, or something over 2. And in this case, this is another example of that. When you're remember your position thing, if your initial position is 0 and initial velocity is 0, then the position of an object would be 1/2 acceleration due to gravity times time squared. If the time was squared, you precede it by 1/2. Same thing here. Kinetic energy is always 1/2 mv squared. Now let's talk about the units for this. 1/2 doesn't have a unit. That's just a number. What's the unit for mass? Unit for mass. What do we measure mass in? What unit? Kilograms. Perfect. How about velocity in the SI units? Meters per second. Okay? But you're squaring that, so that would be meters squared per second squared. And what's a kilogram meter squared per second squared? A joule, exactly. It's the same unit as work, same unit as potential energy. Joule. All energy is measured in joules, or foot-pounds per second. No, foot-pounds. Okay? Okay, well, the name of it is Joule. Don't spell it like a joule like this. It's a Joule, named after James Prescott Joule. Okay. Now, they have an example, and they showed the picture in the book. I don't have one here. Actually, the next slide does look sort of like it, though we're coming back to that, but it'll be destroyed by the time we get back here. This is a pile driver. Now, it's not quite the same as the picture in the book, but it's somewhat similar. Okay? Now, it says a pile driver shows the relation between the energy of motion to useful work. The energy of the driver is its kinetic energy as it hits. Okay? When the driver strikes the pile, this is the pile driver here. Let me go from current slide. This is the pile driver, the big green thing here. Let me get my color back to this. This is the pile driver. When it hits down here, that is that's when it's doing the work. Okay? Now, there's several things going on here, and this is getting a little bit ahead of where we are now. But let me, since the picture's showing it, when it's holding here, the height that it's going to do work under is the height above the pile. Not above the ground, but above the pile. Okay? So here's its mass times its acceleration due to gravity. That's its weight. And that times the height, that's going to be Up here it's gravitational potential energy. When you release it, when they pull the thing and let it fall down the tube here, the potential energy changes to kinetic energy. Right before it hits the POW, it has its maximum kinetic energy. That's the energy that does work driving that into the ground. Okay? That's the concept here. So here's the formula they give with that. So let me get out of here. We're going to come back and see this one again. And I sort of, they're talking about the pile driver here. The energy right before it hits the pile, I don't know where my pen went. Okay, there it is. Okay, energy right before it hits is kinetic energy, which is 1/2 mv squared. Okay, the amount of work that it does is the force times the displacement. Remember, that was our force, that was our work formula, force times displacement. So when the energy of the falling pile hits that and drives it into the ground, that's going to be the force times the displacement. Okay? Now, the whole reason for that is to set up to do example 2. A pile driver with a mass of 10,000 kilograms. Okay? So I'm going to try to draw this. Here's the pile driver. I'm just going to show it here. So the mass of the pile driver is 10,000 kilograms. That is a lot of mass, folks. That is approximately 10 tons. It's actually more than 10 tons. That is heavy, okay? 10-ton thing here, okay? Now, it's going to drive down onto the pile that it's trying to drive here, and the distance it's going to drop is 2.0 meters. The S here is 2.00. No. I can't read. I can't. Oh, that's not what I want to do. Okay. Hit the wrong key here. Okay. I need my eraser. Okay. It's not 2 meters. It's only going to drive it into the ground 0.2 of a meter. 0.200 meters. That's as far as it's going to drive, because this is hard stuff to drive it into the ground. So it's only going to go 0.2 meters. Okay? Its mass was 10,000 kilograms. Its velocity right before it hits that is going to be v is equal to 10 meters per second. It doesn't seem that fast. I'm sorry, that's 10.0 meters per second. Okay? Now, the question is, how much force does it have when it hits the pile? Okay? I'll tell you something. It's going to be a pretty big force. Okay? Well, here we have 1/2 times the mass, which was mass of 10,000 kilograms. That's a huge mass. Okay, now we are going to take half of it, so I'm going to make that 5,000. Okay. Times the velocity squared. Well, the velocity was only 10.0 meters per second, but we're going to square that. Okay, so this comes out being 5,000, half of 10,000 kilograms, times, and what is 10 squared? Anyone know? Yep. 10 squared. 10 times 10. 100. 100 meters squared per second squared, because you square the number, but you also square the units. And this is equal to your force, that's the thing we're looking for, okay, times the displacement. 0.200 meters. So how do we find that force? I'll go on and multiply these together. That gives us 500,000 kilogram meter squared per second squared. That's also joules. That's equal to force times 0.200 meters. Okay? How do we determine the force? How do you undo the multiplication? Divide by the 0.200 meters. And that divides here by 0.200 meters. Okay? Well, what I'm going to do here is move this decimal one place this way and move this decimal one place that way. Okay? Same direction. And do 2 into 50 will be 25, 0, oops, I don't want the comma there. 2, 5, 0, 0, 0, 0, 0. That's 2.5 million. Now, look at the units. This was meter. That wipes out one of those meters. And this is a kilogram meter per second squared. Does anyone know what that is? Kilogram meter per second squared. Think back, chapter 5. What were we studying in chapter 5? Say again? A Newton, exactly. That's the unit of force, which is Newton. So this is 2.50 million newtons. Okay? Or you could say 2.5. The metric prefix for million is mega newtons. Now, most of the time they don't do that. By the way, it's 2.50 because you have 3 significant digits there. 2.50 meganewtons. But a lot of times newtons you just use 2.50 million newtons. Okay? See how they write it in the book. How they get away with it here is 2.50 times 10 to the 6th newtons. Because you move your decimal 1, 2, 3, 4, 5, 6. 6 places, so it's 10 to the 6th newtons. Make sense? All right. Ready for example 3, or do y'all want a little more time writing on that? Okay, take your time. Now, I'm doing this division in my head, so that's why I'm moving decimal places. You got a calculator, just plug it in. You should get the same thing unless I make mistakes, which I do. Okay, so let's move on to example 3. A 60 gram bullet. 60.0 gram bullet. Now, what's that a measure of? Say again? What does gram measure? Mass. That's your mass of the bullet. Now, it's not in SI units. If it was in SI units, what will you have to have? Kilograms. So how would you get the 60 grams to be kilograms? We've done it several times tonight. How many places? 3. So that you have to put a 0 in front of that, and that would be 0.060 kilograms. Okay. Now, Actually, it's 0.600 kilograms because you got 3 significant digits. Those zeros in front of the 6 are not significant. The ones after the 6 are. 0.600 kilograms. It's fired from a gun with 3,150 joules of energy. Now, how they knew that, I don't know, but this is joules of kinetic energy. It says E sub k, kinetic energy. Find the velocity of that bullet. Say that again. E sub k is, yeah, and what is that equal to? 1/2 mv squared, right? That's the formula. And it's really good you saw that, because now what you're trying to solve for is velocity. So what we have to do is multiply both sides of the equation by 2 to get rid of the half. So that's going to give us 6,300 joules. Now let's get this in fundamental units. What is a joule? It's a kilogram meter squared per second squared. Kilogram meter per second is a Newton. Kilogram meter squared per second squared is a joule. Okay? So we multiply both sides by that. And so that's equal to mv squared. We're trying to solve for v here. That's what we're looking for. What is the velocity of the bullet? Okay? Well, we also need to divide by the mass. So let's divide by the mass, but the mass, oops, it's pretty ugly. The mass was 0.060 kilograms. And you see why it's important that we change the grams to kilograms? Because you need that to cancel out here. Okay? Now this time I'm moving my decimal place 2 places here, 2 places there. And 6 will go into 6 1 time, 6 will go into 3 0 times, 6 will go into 35 times, and you still have 3 more zeros. So that's 105,000, the kilograms canceled out, meters squared per second squared. That's your v squared, because you divided out the mass. But I don't want to know what v squared is. I want to know what v is. I want to know the velocity of the bullet. So how do I do that? Nope, not quite. It's similar, but not quite. How do you undo a square? Huh? No. That's getting further. Okay, we haven't done it yet this term, but it's something hopefully you've done sometime in the past. Undo a square by taking a square root. Ever done those? A long time. So what you do, you take a square root to get the v. So v would be, take a square root of 105,000. And I'm just going to make a guess here. That's going to be something around 300 and some odd, I think. I don't know how many, 350 or something like that. Don't worry with what I'm doing. You, on your calculator, take a square root of 105,000. Okay? My guess is going to be around 350, but I may be wrong there. Say again? 324? 324, and you take the square root of the units too, and that would give you meters per second, which is a great unit for a velocity, right? Okay, on the calculator you mean? I think she read it from the book, is how she did it, didn't you? Huh? Oh, you had already done it? Okay, let me see the calculator. Okay. Okay. All right. I need my glasses off for this. Okay. Look for the square root right there. Okay. Ah, there you go, 324. Okay. So 324, so take the square root of the units as well. Square root of meter square root would be meters, square root of second square root would be second. So that would be meters per second, which is exactly what we measure velocity. Yeah. And let's see what they got. 324 meters per second. Now, one of the reasons that I remember when we were doing potential energy, and they said, just called it E sub P, and they said that's gravitational potential energy. I said, no, that should be called E sub GP for gravitational potential energy. Because there's other forms of potential energy that are based on position. And one of those is the spring potential energy. Okay? If you think about a spring, you've probably done this before. If you pull on a spring, it pulls back, right? In the opposite direction. Or if you compress a spring, it pushes back in the opposite direction. Okay? Sort of like me rocking in this chair. It doesn't have much spring to it, but a little bit. Okay? And that's another kind of energy of position. It's called elastic potential energy or spring potential energy. That is, again, a type of internal potential energy. The guy who worked on that was a guy named, Robert Hooke, and they mention him here, and they talk about the different kinds. They don't give you any formulas, they just talk about it. And they say it's talked about in chapter 12, section 12.2. We're not, I don't think, going to do that. I don't believe chapter 12 is one of our chapters, is it? Yes, it is. Yes, it is. Okay, so we'll be doing that. In fact, that's the next chapter we do. So we'll come back to that later. So they talked about two types of energy, kinetic and potential, but potential could be gravitational potential energy, spring potential energy, or elastic potential energy, chemical potential energy. There's lots of different potential energies. But when you talk about motion, gravitational potential energy or spring potential energy and kinetic energy, the two of those added together form what they call mechanical energy, the sum of potential plus kinetic. Okay? They haven't talked about that yet, but it's going to come up. There are many other forms. Chemical energy, again, that's a type of potential energy. Atomic energy, that's potential. Electrical potential energy, sound energy, heat energy. There's tons of different kinds of energy. And that finishes 8.3. So your homework exercises there would be either 1 or 3, and then any of the odds 5 through 21, and do several of those.
Either 1 or 3?
Oh yeah, or both. If you choose, if you find out, oh, I need more work on that, then do that. Actually, they talk about two different things. One is potential energy and one's kinetic. You may want to do both of those. Okay, and then do some of the other odds 5 through 21. Okay. Now, we don't have a whole lot of time left, but we do have a little bit. So you want to give it a shot to start 8.4? Okay. And this is where we finally get to our pile driver that I showed you a little bit earlier. So I'm going to erase this, and the law of the conservation of mechanical energy. Now, by the way, all energy is conserved. Total energy is always conserved. The trouble is it changes its form so easily, it's hard to keep up with what form is what. But here is the law of conservation of mechanical energy. And here is what I just said earlier. The sum, and sum means what? What operation are you doing when you sum? Adding. The sum of the kinetic energy, let's see, let's call it E sub k, okay, and the potential energy, and this time I'll let them get away with E sub p because it can be any potential energy, in a system is constant. Okay? And if no resistive forces do work. If no resistive forces do work. Now, in reality, that's not always happening. Because when you picture these pile drivers here, that pile is falling down that tube. If you can hear it fall, it's scraping the sides, there's some friction there. Now, if they keep those sides really well lubricated and stuff like that, you minimize that. But there's just about always frictional losses. So most of the time, the law of conservation of mechanical energy doesn't hold just because you always have some resistive forces, resistance. Okay? Now, let's go back to the slide we were using before. Okay? This may be about all we have time for. We've got 6 minutes. So let's see what we can do with this. Okay? Now, remember, oops, let me get my pen back. Okay. Potential energy, what was that formula? Gravitational potential energy? mgh. Gravitational potential energy, mgh. Think of it, because the acceleration due to gravity is in there, so it's gravitational potential energy. Okay, where this is your h, the height that the pile driver dropped, the mass is whatever the mass was, the g is the acceleration due to gravity, so mg is the weight of that pile driver, either in pounds or in newtons. Okay, the height that it drops, that's going to be the h there. Now, when you're up here, your gravitational potential energy is at the maximum. You pulled it up with your crane, cranked that thing up, got it to the top of that cylinder, and what you're going to do is let it fall. And when it falls, it's going to go down there. So the amount of gravitational potential energy is the maximum right there, and that's your mgh, where h is the maximum height above the top of the pile. Now up there at the top, is it moving? Not yet. When you release it, it starts moving. So at the top, if it's got no motion, it has no kinetic energy. Because kinetic energy, what was its formula? You just told me a few minutes ago. Yeah. Told me just a few minutes ago. Or maybe 10 or 15 minutes ago. 1/2 mv squared. You just told me that, remember? Okay, that's your kinetic energy. Kinetic means it's moving. If it's moving, it's got a velocity. So think of that anytime you see kinetic, velocity's involved. Anytime you see gravitational potential, gravity's involved. The g is involved. Okay. Now, the next figure shows what happens when it hits. Right when it hits now, your potential energy is going to 0 because the height above the pile is 0. You're on top of the pile now. But now your kinetic energy is at the max. Right before it hits, that's the maximum speed it'll have, so therefore it's the maximum kinetic energy. Okay? And again, this is 1/2 mv squared. Now, I meant to show here. Up here, your velocity is 0. So that's why the kinetic energy is 0, because you haven't released it yet. Or even when you just release it, its initial velocity is 0. But when it hits the pile, it has the maximum velocity, so therefore it's maximum kinetic energy. But this, which is mgh, the h is 0 now, because it's at the top of the pile. There's no height above the pile. So at impact, the potential energy is 0, but your kinetic energy is at the max. Okay? Now, what this means, if we combine those two figures together, the sum of these two is what? The sum of kinetic and potential energy is what? From my previous slide. I've already erased it. Remember what that was? I'm going to call it E sub m, mechanical energy. The sum of those is the mechanical energy at the top, and at the top it's all potential. The sum of those down here, it's all kinetic. But the mechanical energy, this is E sub m down here, those are the same because it's conserved. As long as there's no frictional losses there, it's conserved. And if it's conserved, that means it's the same. So that means, let's see if they do the next slide. No, they don't. That means, what's that?
Why does the book has, when it has E sub k equals 1/2 mk v to the second equals 1/2 m 0 second power equals 0. What is that?
Okay. That's this place back here. That's what we were just talking about. Up here at the top, when you're holding it there, the velocity is 0. So plug in 0 here, you get 0 there. Because velocity is 0. Okay? Down here, the potential energy is 0 because your H is crowned to 0. See, the H was up here, and now the H is 0 because it's not above the thing. So now your maximum kinetic energy, 0 potential energy. In the first case, it was 0 kinetic energy, maximum potential energy. And because this is EM at the top and EM at the bottom is down here, and the mechanical energy is conserved, they must be the same. So therefore, and this is what it's getting at, the maximum at the top was mgh. So mgh at the top is equal to 1/2 mv squared at the bottom. They have to be the same because mechanical energy is conserved. Now what they're going to do with that is solve for v. So the first thing they're going to do is multiply by 2. So that gives you 2 mgh is equal to mv squared. Then they're going to divide by m, and look at what happens then. Your m goes out here, and it goes out here, and now you have v squared is equal to 2gh. And how do you undo a square? Take a square root. So your velocity at the bottom is the square root of 2gh. That's the formula they have there. That's the bottom of page 219, and we're right ready to do the example at the top of page 219, but I think we're out of time, aren't we? So we'll start there next time, at the top of page 219. All right, any questions? All right, good deal. So, I think you probably did. And by the way, yeah. Okay. Well, I mean, you can ask anytime. But let me say this. Remember, we said we'd meet until 7 on Thursday of this week and Tuesday of next week, and then we'll go back to 6:30 in time, right? Okay. All right. So I'm going to go on and stop this. I basically said that for Haley's sake because she wasn't here. If she does listen